Amine corrosion in acid gas treating systems, understanding corrosion challenges in gas treatment processes. Overview of amine corrosion. Amine corrosion occurs in equipment used for acid gas treating processes where amines such as monoethanolamine (MEA), diethanolamine (DEA), disopropanolamine (DIPA), and methyldiethanolamine (MDEA) are employed to remove CO2 and H2S from hydrocarbon streams. These systems are critical in oil and gas refining, natural gas processing, and petrochemical operations. Corrosion in these environments is primarily driven by the interaction of acid gases with amines, forming corrosive salts like carbamates and bicarbonates. The severity of corrosion depends on several factors, including acid gas loading, operating temperature, amine type, and the presence of degradation products. If not properly managed, amine corrosion can lead to equipment failure, costly downtime, and safety hazards. Understanding the mechanisms and contributing factors is essential for selecting appropriate materials, implementing preventive measures, and ensuring reliable operation of amine treating units. Key corrosion factors influencing amine corrosion. Several key factors influence the rate and severity of amine corrosion. Acid gas loading is a primary driver. Higher concentrations of CO2 and H2S increase corrosivity by forming corrosive salts. Temperature also plays a significant role, as elevated temperatures accelerate chemical reactions and corrosion rates. The type of amine used affects intrinsic corrosivity. MEA, primary amine, tends to be more corrosive than DEA, secondary, and MDEA, tertiary, although all can become problematic under high acid gas conditions. Degradation products such as heat-stable salts, HSS, and other breakdown compounds significantly increase corrosion potential. Oxygen ingress is another critical factor, as even small amounts can drastically increase corrosion rates, particularly with MEA. Mechanical factors like high fluid velocities contribute to erosion corrosion, while high-stress areas such as welds and heat-affected zones are vulnerable to stress corrosion cracking. These factors often act synergistically, making corrosion control a complex challenge. Common corrosion manifestations, types of corrosion in amine systems. Amine systems exhibit several forms of corrosion damage. Stress corrosion cracking, SCC, is a major concern, particularly in stressed carbon steel such as a 516Gr70 exposed to MEA or DEA, often occurring in rich sections of the system. General corrosion is common in areas with high acid gas content or inadequate protective measures, leading to uniform metal loss and reduced equipment life. Erosion corrosion occurs where protective iron sulfide films formed by H2S are stripped away by high fluid velocities, exposing fresh metal surfaces to aggressive environments. These manifestations can lead to leaks, equipment rupture, and significant operational hazards. Identifying these patterns early through inspection and monitoring is crucial for preventing catastrophic failures and ensuring safe operation. Mitigation strategies, preventive measures for amine corrosion. Effective mitigation of amine corrosion requires a multifaceted approach. Material selection is critical. Stainless steels and specialized alloys should be used in high-risk areas such as regenerators and heat exchangers. Post-fabrication stress relief for carbon steel components helps reduce susceptibility to SCC. Operational limits must be carefully controlled, including amine strength, lean/rich loading, and operating temperatures. Corrosion inhibitors can be added to reduce corrosion rates, while continuous filtration systems help remove degradation products like heat-stable salts. Process control measures such as monitoring CO2 or H2S ratios are essential, as higher H2S levels can form protective sulfide films that reduce corrosion. Implementing these strategies in combination ensures long-term reliability and minimizes the risk of equipment failure. Amine specifics, comparison of MEA, DEA, and MDA. Different amines exhibit varying levels of corrosivity and operational characteristics. MEA offers high absorption capacity but has the highest corrosion potential, requiring strict loading limits and careful monitoring. DEA forms carbamates and can be more corrosive than MDEA, especially when degradation products accumulate. MDEA, a tertiary amine, generally has lower intrinsic corrosivity and is preferred for selective H2S removal, but it remains susceptible to corrosion when CO2 is present. Understanding these differences is vital for selecting the appropriate amine for specific applications and implementing tailored corrosion control strategies. Operators must balance absorption efficiency, corrosion risk, and operational constraints to optimize system performance. Key takeaways, summary, and recommendations. Amine corrosion is a complex phenomenon influenced by chemical, thermal, and mechanical factors. It poses significant risks to equipment integrity and operational safety in acid-gas treating systems. Effective management requires understanding the underlying mechanisms, selecting appropriate materials, controlling operating conditions, and implementing preventive measures such as inhibitors and filtration. Regular monitoring and inspection are essential to detect early signs of corrosion and prevent catastrophic failures. By adopting a comprehensive corrosion control strategy, operators can ensure reliable performance, minimize downtime, and extend the service life of critical equipment.